Hi everyone, this video is going to cover sections 1 to 10 of chapter 7, so an introduction to the chapter as well as some nomenclature. In this chapter we're going to add elimination and substitution reactions. For both of these reactions we have to have, and we define a substrate as a carbon group bonded to a leaving group. And our carbon group has to be sp3, and our group is usually a halogen. We're abbreviating it as an X here, but that's not a requirement. We'll talk about other options. We're going to react our substrate with Y. Now, it has to be negatively charged or partially negatively charged, and it can act in two different ways. Acting as a nucleophile, then our reaction through a substitution reaction. The halogen is a leaving group, so there's our leaving group after it's left. Our nucleophile is now bonded to a substrate, so the Y has substituted the X. If the Y acts as a base, then our reaction will go through an elimination reaction. Our leaving group leaves, and our base is going to remove hydrogen from the vicinal carbon, the carbon next to our halogen carbon, and we will make an alkyl double bond. So it's placed by the nucleophile, and in elimination, the group leaves, and with that base, and we create alkene. Bases and nucleophiles are very similar. They're both negatively or partially negatively charged, and so because of that, some reagents can do both. So for example, in this reaction we have our carbon substrate bonded to a chlorine leaving group, and we're reacting it with sodium hydroxide. Now we know that sodium is just ion, so really when we see sodium hydroxide we want to think of it as hydroxide ion. This goes for any time we see sodium or potassium bonded to an anion. If we treat our hydroxide nucleophile, or think nucleophile, then it's going to go through a substitute and replace that chlorine to create this alcohol group. If we think of our hydroxide as a base, then it's going to remove that vicinal hydrogen, so the hydrogen on this carbon right here, and the leaving leaves, and we create our elimination product. Now the two side products over here, the Y from the hydroxide bonding to the hydrogen of that carbon, and we have our as our leaving group, and then that sodium as that spectator that we started with. So part of our job in this chapter, by the time we get to the end, is to decide which pathway will a group of reagents take, especially if our reagent can act as a nucleophile. When this case occurs, sometimes our reagents can go down one pathway, and in other times they can go down two pathways, meaning it could be an elimination or a substitution, and in cases we will have to decide what the major product is. Now our substrate is this carbon that is bonded to a halogen. So we want to talk about the purpose of this halogen. And over here we can see that our carbon bonded to our halogen is creating our partial positive charge. We know that this is happening because our halogen is electronegative. It's withdrawing those electrons through induction, creating that partial positive charge. It makes our electrophilic, which also means that it's going to be reactive with a nucleophile. So that's our first reason why we have a halogen on there, is it makes the carbon more reactive. The second reason why we have that halogen on there is because it is a good leaving group. So the table that's on our slide includes acids on the left, and we've seen this portion of the table before. We have our strong acids up at the top and our weak acids down at the bottom. We also know from Gen Chem that strong acids create weak bases, or another way to say that is a stable base, aka a weak base, is a. So the ions that are in this top table here are our good leaving groups, and the ones in the bottom table down here are the bad leaving groups. Notice in our good leaving groups, halogen, this large sulfone we'll talk about later, and water. These are what we want to look for as we're doing these reactions. So halogen's two jobs: making that carbon more reactive and being a good leaving group. We use a couple different labeling techniques as we talk about these. The first way is using Greek letters. So the carbon bonded to our halogen or bonded to our leaving group is referred to as the alpha carbon. It's just so we can say the alpha carbon instead of saying the carbon bonded to the halogen. So it just makes the language a little bit cleaner. Same thing with the rest of the letters. The carbons next to the alpha carbon are the beta carbons, and carbon next to that is gamma, and we could keep going to delta and so on. And again, it's just a way for us to say the beta carbon instead of saying the carbon bonded to the carbon bonded to the halogen. It just makes the language a little easier. We classify that alpha carbon even further based off of how many carbons it is bonded to. So the three labels on the bottom here we've seen before. Here's our alpha carbon. It is bonded to one other carbon, and so we label it as primary. Our alpha carbon here is bonded to two carbons, so we can label it as secondary. And last alpha carbon example here is bonded to three other carbons, so we can label that as tertiary. Because we're adding halogens to our alkanes, we also want to be able to use nomenclature with them. Thankfully, when we add in nomenclature in organic chemistry, the rules don't change, we just add on to the rules. So we know that our first rule is that we want to find parent chain. We know that this is the longest chain within our structure. Our second rule, or second step, is that we want to find all of our substituents. The third step is that we want to number that parent chain, and we want to use the lowest numbers possible. And then the fourth step is that we put it all together, and when we do that, we want to make sure that we're alphabetizing our substituents. With our new halogens, we end them with an O: chloro, fluoro, bromo, and iodo. And so we incorporate those just like we would any of our carbon-based substituents. So for example, in this bottom one over here, we have a 5-carbon chain. On carbon number 2, we have a methyl and a bromo. So when we put all that information together, we get 2,2-methyl pentane. Bromo comes first, it's alphabetical. So let's do a practice one. So let me draw a structure for us here. All right, so that's what we're going to practice with. And so we know that we need to do some numbering. We need parent chain. And so as we look at it, we can number across 3, 4, 5, 6, 1, 2, 4, 5, 6, 7, 1, 2, 4, 5, 6, 7, 8. So definitely just this straight across chain is the longest one. And then we need to decide if we're going left to right or right to left. So if we go from left to right, we have 1. Substituents are on 3 and 5. And the other side, 1, 2, 3, are substituents. So we definitely want to number left to right in this case. As far as our substituents go, we know that we have a methyl and an ethyl, and our new one is our iodo. So alphabetically, we know that we're going to do our ethyl first, followed by our iodo, and then our methyl comes in last. The other information that we have here is that carbon number 4 has a wedge on it, and it's a chiral center, so to include its stereochemistry, so meaning an S. So I'm going to include a spot to put that, but we'll figure that out in a second. I'm going to say 5 4 iodo 3 methyl octane. And then that last piece of information is we need to know if that chiral center is RS. So when we look at what's attached to carbon number 4, iodo is definitely highest priority atomic number. And then attached to that carbon 3 and carbon 5. Carbon 5 is going to give us it will continue going after carbon 3 runs out. And what I mean by that is if we compare 3 and 5, they're both CHs. They each are bonded to 2 carbons. Continue down the line, and when we hit carbon 1 and carbon 7, that's where our difference. This is a CH2 bonded to another carbon, and this is a... So carbon 5 is our higher priority compared to carbon. The 4th priority is the hydrogen that's not shown, so we don't have. And as we go from 1 to 2, 3, we're going to the, which tells me that to be an R. Now, on that same note, there is more than one chiral center in this structure. Carbon 3 and carbon 5 are also chiral centers, but we're not given any information about their 3D shape. We're not wedges, so we can't include that in the name. Even though we're only including one chiral center in the name, we do still need to include. We just said R, 4-iodooctane, that R needs to be included in the structure. So giving this enough to be able to complete drawing from the name and vice versa. So we do like to talk about real-world uses or real-world occurrences of our compounds. And so this is looking at where we would find alkyl in the real world. And so there's a couple examples on here. DDT up at the top there is in some mosquito repellents, and lindane over on the side is used in lice shampoos. So those are both of those fall under insecticide types. And then the one that has the 3 fluorines attached is fluoxetine, which is the common name for Prozac. And then underneath that, there is one of the repellents, the Guam bubble snail, is shown there. So that one is definitely in the naturally occurring category. We have our pharmaceutical, our fluoxetine, our Prozac, and then the category there is cis precursors. As we talk about reactions in this chapter, we'll see how we can turn an alkyl halide into a lot of different functional groups. So these are used as the starting point for a lot of other reactions. So we're going to section 7.7, and in this section we're looking at alkenes, specifically their nomenclature, a little bit about stability. And so we are jumping to a higher section, but it is still about nomenclature, so I thought that they would go together. Like, we're keeping that same set of steps. We're looking for our parent chain, we're giving the low numbers, we're looking for our substituents, and then putting them together alphabetically. When we're doing this with alkenes, there's 2 more that we need to know. Our parent chain is going to end in -ene. So instead of an alkane, instead of pentane, we're going to have pentene. And we're going to put a number in the front of that to tell us where that double bond is. And then in front of that, we will include E, Z, cis, or trans, depending on what type of double bond we're dealing with. Now, one of the nice things about naming double bonds is that because we've incorporated a functional group, we have a double bond, our functional group is going to get the lowest number possible. We don't need to look at the rest of the substituents to make this decision. We only have to look at where the alkene is located. So we're going to do a couple practice ones with this, and we're going to start So we're starting very small, but it's important just to know our basics. So we have a 5-carbon chain, and we're going to number it because we want that double bond to be between carbons 2. If we numbered it from the other direction, 1, 2, 3, 4, 5, our double bond would be between 3 and 4. So it be as low as possible. When we name this, we're going to first number the lowest number or locant, or find our double bond. And so there's actually 2 ways to do this. We can write 2-pentene. So that tells us that we've been, and at carbon number 2, there's a double bond. We can also write pent to ene. So it's dividing the name up to say we have 5 carbons and we have a double bond at carbon. When we have a simple structure like this, it's just 2-pentene is definitely going to be the more common option. More functional groups, more substituents, we get more complicated molecules, it's going to be more common to divide it up a little bit. It isn't complete. Because of the stereochemistry of bond, we also add in trans to our name. So this is trans 2-pentene. All right, let's do something a little bit larger right here. We're going to name. And first step is we want to find that parent chain, and it should include the double bond and our the lowest number possible. So because it is located, I know that I'm going to start. And so as I start to number it, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So I know we're going to go down this chain here. What's attached? What are substituents? We have a chloro, and then attached to carbon 6 here, we have an isopropyl. And we know that iso counts when we're alphabetizing. In this case, it actually doesn't matter because chlorine to come first. And so that's how I'm going to start my name for this one. I'm going to start it with that chlorine. So we're going to say 3-chloro, 6 isopropyl, 3 nonene. So none because there are 9 carbons, ene because there's a double bond, and that double bond is at carbon number 3. I want to say what my stereochemistry is for that double bond. We don't have 2 hydrogens attached, so trans. So we want to use Z. So remember, with cis and trans, we need to have 2 hydrogens, a hydrogen. So this is where we have our priorities again. So if we look at carbon number 3, the chlorine is the hydrogen substituent. On carbon number 4, it's not drawn in, but we know that this portion of the molecule will be the higher. Our 2 higher priority groups are inside, so we're going here in the front. So our final, out here in the front, Zizamzide. 3-chloro, 6 is our final name for that alkene. Okay, we're going to do one more of this, one that incorporates a center as well. We can put that in the name. So here's we also have 2 double bond structures. So this is going to look at double bonds as well as a dash attached to it. So we have to decide which way we want to number this from. 1, 4, 5, 6, 7. 1, 2, 3, 4, 6, 7. Double bonds are on carbons 2, so that can't be our deciding factor. double bonds, that should be the first thing we look at. It's not going to help us. So we have to look at our other substituents. With the red numbers, our halogens are on, and with the blue numbers, they're on 3 and 4. So just like that, we can eliminate those red numbers because the blue numbers are smaller. Alphabetically, our chlorine. So I'm going to leave some room over here, but we're going to start with 3, 4, fluoro. We have a 7-carbon chain. We know it's hept. We have alkenes, so ene, but 2 alkenes. So we are going to call this heptene. So the hepta is 7 carbons. The di alkenes, there's 2 double bonds. We do need to say where they're located. So right here in the front, we're going to say 2, 5. So that's carbon 2 and a double bond at carbon 5. Now, we need a lot of information over here. It's the glare from my dining room light. There we go. Carbon 2 and double bond. Carbon 5 and 6 have a double bond. And carbon. So let's just go in order. I'm going to put a 2, and then we're going to put a in there. So if we look at carbon number 2, we have a methyl group, and this one is my higher priority. And when we look over here, the chlorine is my higher priority. So this falls under the E category. My 2 high priorities are opposite one another. We want to say what is located at. So our fluorine is our 5 and carbon 3. They're both carbons. Carbon 3 is bonded to 2 chlorine. Carbon 5 is bonded to 2 carbons. Helps this side win. So 1, 2, 3. So we do 1, 2, 3. Going to the right, but our lowest priority hydrogen is in a wedge position. Going to the right, and it's going to turn into an S because of where our hydrogen is located. That right there is part of our name. And then the last thing, parenthesis over a little bit, we're going to have a 5. And then at carbon number 5, we do have a hydrogen at each trans to describe there. So our full name for this is 2E, 4S trans, 3, 4 fluoro, 2, 5 heptadiene. Very long, but it's because there's so much sterile information within the structure. So the second half of the section is looking at the ability of these double bonds. And really it comes down to 2 things. Our double bonds are more stable when they have more carbons attached to them. So our monosubstituted are the least stable, followed by di, and then tri, and then tetra. The second thing that plays into stability, trans versus cis. And when we're talking about trans and cis here, we're really talking about whether the large groups are close together or not. Not necessarily the way that we've been labeling them. So within that di category, our would be on the more stable side, and then our cis would be on the less stable. And this has to do with steric strain or steric hindrance that we've talked about in other chapters. And then this chapter is looking at our rings. When we have a ring of carbons that is 6 or less, our double bonds can be in the cis formation. 7 or more carbons, it can be cis or trans, and so that would need to be stated. If we have one of our smaller sized rings, so 6 or less, it doesn't have to be part of the name because we can know that it can only be cis. So 7 or more, we would have to say cis or trans. Both or either is it has a little bit more flexibility, so there's more freedom of movement. All right, that is it for this video.